Well, welcome everyone to the ENC 2023 Wednesday evening Ivan Hour. Glad to have everyone with us tonight. This is officially Ivan meeting number 51.
That's right.
Since we started in 2016, we're very happy that everyone is here this evening. Ivan meeting number 3 for, actually Ivan meeting number 4 for ENC this year. You know, of course, we had our all-day Saturday meeting, and then Monday, Tuesday, and then Wednesday tonight. And very, very interesting topic tonight. Of course, Monday, we had a very nice talk on astronomy. Tuesday for the old-timers, and I was told not to say old-timer, but I promised I would not say old-timer, but I don't know it. I always say the wrong thing. But anyways, this evening is, I'll describe it as being application of NMR in the world of fine art. And we have, well, I'm going to let Dave do the introduction.
Okay.
Dave is much more versed in what goes on with this. I'll give it to you, Dave.
Okay, very, very good. Okay, so our speaker tonight is somebody that many of us know from many ENCs, Nick Zumbalyadis, and he for many years, I've known him at ENCs. He was a longtime employee of Kodak, doing solid-state NMR of many different things. And on his retirement, he decided to take up the project of applying solid-state NMR to the issues of art restoration. And so, and began basically a second career in that subject. And he's had a number of NSF grants for it, and has worked, one of his collaborators is Cecil Dabowski, I guess, at University of Delaware. And so, and I'm looking forward to having a nice evening discussing art as well as NMR and chemistry. So let me hand things over to Nick.
Yeah, thank you, Dave, for the introduction. Can you hear me all? Is everything all right?
Yes, very good.
Yeah, okay. Thank you very much, Dave, for the introduction. As you said, after retirement, I got initially out of sheer curiosity into this world of cultural heritage science, just to find out what this is all about, and it evolved in some sort of a second career, from a post-retirement second career. And so I would like to tell you a little bit about what I've done in that area in collaboration with my colleagues, because we're actually a team. I'm not a one-person operation. We are a core team. I noticed Cecil was online. I don't see him anymore. And of course, our partner Sylvia Centeno at the Metropolitan Museum of Art. So let me actually begin sharing my screen. Okay. Well, if you look at the organizational chart of any famous museum, besides the regular curatorial departments like antiquities and Asian art and European paintings or whatever you, and of course the body of art restorers and object conservators, whose job is to maintain those objects and keep them look nice. There is always this other department, fairly sizable and fairly well equipped, and it always goes under the name of the scientific research department. So every major museum has what they call a scientific research department. And I was very curious to see what goes on in that. And that's how it all started. What goes on in there is cultural heritage science, a science for which, in fact, there is a Gordon Conference. There is such a thing as a Gordon Conference for Cultural Heritage. And gradually I became involved in that, and that's the story I'm going to tell you. But before I define cultural heritage science itself, we need to go back one step and define a term that may not be familiar to all of you, and that's what we call material culture. The textbook definition of material culture in the humanities essentially says it's everything. Material culture refers to the physical aspects of a society, the objects, specifically the objects made or modified by humans. And these objects surround people and their activities, and they are defined by their properties, be they chemical, biophysical, or even biological. And the objects do not exist in isolation. They interact with humans, and that's when they also acquire meaning. And they can be quite diverse objects, large and small, from a page from an illuminated manuscript to a painting by, on a ballet painting by Degas, to cave paintings, to cave paintings from prehistoric times in Lascaux, all the way to very large structures like the Great Wall of China. They're all part of the material culture. And cultural heritage science, then, is the in-depth scientific study of the material culture using various physical, chemical, and biological characterization methods, recently augmented by computational methods and other information technology tools. So you can ask, well, what is really the upshot of this work? Why do we do this, and why do we learn? And I think we can categorize, we can divide the outcome of this research into three categories. The first two are the bread and butter of the business, the ones that pay the bills. One is to establish objective criteria for the dating and authentication of artifacts. That no museum likes to display fakes, of course. Secondly, is to develop the science to support the work of object conservators. Object conservators undertake some very drastic interventions into those objects, and we have to make sure that we understand the chemistry and physics behind what they do, so that they don't do more harm than good. But there's a third category which I find most interesting, and that is to address questions in cultural history, broadly defined. For example, origins and trade routes of materials, artisanal practices and recipes, emergence of new materials over a period of time, changes in materials processing, and the choice and use of materials for war, peace, and ritual. After all, the choice of steel, for example, to make a weapon, they chose quite a different type of steel than was used for other objects. Anyway, human activity is infinitely diverse, and so the list is virtually inexhaustible. If you're doing research in this area, you'll never run out of projects. Well, it is not a particularly new branch of science. I think that Sir Humphrey Davy is probably, in my judgment, the first cultural heritage scientist. Even though there were some attempts before him, Humphrey Davy wrote this seminal paper published in the Philosophical Transactions of the Royal Society in 1815. And the title is Some Experiments and Observations of the Colors Used in Painting by the Ancients. I would like to read to you, it's a fairly lengthy and very interesting article and readily available, but I would like to read to you that one paragraph I singled out, where he writes, "When the preservation of a work of art was concerned, I made my researches upon mere atoms," he meant very small amounts, "of the color, taken from a place where the loss was imperceptible, and without having injured any of the precious remains of antiquity, I flatter myself I shall be able to give some information not without interest to scientific men as well as artists, and not wholly devoid of practical applications." That's a very interesting statement. In fact, if when you read the whole article, you realize that Humphrey Davy removed minute amounts of material from inconspicuous areas, carried out essays on site, successfully identifying most pigments, compared his results to ancient recipes by Vitruvius and Pliny. That becomes evident if you read the paper. And by comparing the cost of the pigments used in different places, he assigned meaning to different locations within a structure. In fact, he was looking at the wall paintings of the baths of Titus and Livia in Rome, and as well as in some villas in Pompeii. And he by examining by noticing that the most expensive pigments were used only in some very specific areas, he was able to conclude, I think correctly, that those areas, that space, was reserved for the Roman emperor and his immediate associates. So these are the kinds of approaches and strategies you might take even today in cultural heritage science. So this study the scientific study of art is not exactly a new phenomenon. Later on, Edward Waldo Forbes, who was the director of the Fogg Art Museum at Harvard University for almost forever, from 1909 to 1944, according to a colleague, Mary Virginia Orna, adamantly maintained that art and science are so firmly linked that a work of art cannot be understood fully unless without understanding the materials from which it is made. That's a fairly strong statement. Okay, so what are the ideal performance requirements for analytical instruments used in cultural heritage studies? I think there are basically four aspects. The equipment has to be non-invasive, portable, easy to set up, and fast. Actually, in some cases, nano-invasive materials or techniques can be tolerated if the results are expected to be quite unambiguous and incisive. However, I was told by museum people that the rule for sample removal is, if you can see the sample, you have already removed too much. Well, that's a fairly difficult constraint. And yet, here are some examples of what you can learn with these techniques. Here and I'll give you two examples. Mostly one example. And the person you see here is our colleague and co-PI in the research I will describe later, Silvia Centeno, one of the scientists at the Metropolitan Museum of Art. Up there on the left, you see the famous painting of Antoine Laurent Lavoisier, the chemist, and his wife Marianne, as painted by Jacques-Louis David in 1788. The painting that you see is the way it now hangs in the Metropolitan Museum of Art, and it looked always like that too. However, when Silvia Centeno studied this painting in great detail, using large area X-ray fluorescence and scan large areas with it, she realized that behind this painting there is a preliminary sketch that looks quite different. By studying the remnants of paint there, she discovered, for example, that there were no chemical instruments in front of Lavoisier in the original. Here you see Lavoisier sort of looking at some chemical instruments and taking notes, and his wife, dressed modestly standing there in a supportive role. In the original sketch, the table is much more lavish with gold inlays. There are no scientific instruments. And Madame Lavoisier is wearing a very fashionable plumed hat, a very expensive one. And the couple essentially projects their social class, which was an upper level bourgeoisie, very well-to-do, very well-heeled members of nobility. Actually, nobility. However, as the French Revolution unfolded, David thought it prudent to rework the painting, apparently, and make them appear like scientists and his very modestly dressed wife and so forth, but it didn't work. As we all know, Lavoisier was executed at the guillotine. Below, Sylvia is again studying a painting by Van Gogh. That's the real stuff here. What you see there is the real thing, the Van Gogh painting, to define the range of fading of red lake. A lake pigment, by the way, is made by precipitating a soluble dye onto an inorganic substrate to make it insoluble, just parenthetically. So this is the kinds of very interesting information that you can gather by non-invasive techniques. Portability is another factor. Here is actually a view of the Metropolitan Museum galleries of Southeast Asian sculpture galleries. After hours, when the visitors leave, they roll in the X-rays. And what you see here is an X-ray fluorescence setup to examine one of the statues in situ right in the gallery. Well, so obviously, given these stringent requirements, you would expect that nuclear magnetic resonance spectroscopy, I have to be explicit in that, would play a very small role, a little or no role in cultural heritage. Things are not as bad, however, because in archaeology, which is part of cultural heritage science, you can relax some of the sampling requirements. You are allowed to get a little bit more sample. After all, you're not dealing with a single object, you are dealing with an excavation area with all sorts of shards and broken pieces and stuff around, and you may be able to remove a little bit, just enough to do NMR studies. And people have done that for quite some time. And Joe Lambert at the time at Northwestern University reviewed the field of NMR in archaeology up to the year 2000 in a paper in the Chemical Society Reviews. After that, actually quite a few names that we are familiar with in solid state NMR, colleagues of ours, have occasionally worked in archaeological projects. For example, Bob Boto, whom you may know as a specialist on carbonaceous materials and studying NMR of coal for the Department of Energy way back then, has also studied the remnants of charred food remains in Iron Age Roman vessels, and was published in Archaeometry in 2007. Sabine Hediger has one paper where she actually has been part of a study of archaeological leather using both EPR and NMR, published in Analytical Chemistry in 2009. A colleague, somebody we all, I think, we know, at least I know Bernhard knows her very well, Eleonora Del Federico, together with Cindy Caylett, who got her PhD actually at the University of Aarhus from Niels Christian Nielsen and Alexei Yershov, have studied the reindeer skin tanning processes in various tribes, and they using both unilateral NMR, that I will discuss a bit more later, and magnetic resonance imaging. atomic scale compositions of structures that account for the stability of the historic pigment Maya blue were studied in the thesis by Zach Bergson, as part of the thesis of Zach Bergson, who got his PhD from Brett Schmelka in 2018 in Santa Barbara. We should also not forget that other colleagues of ours, like Warren, has done not using NMR, but his other technique, the probe pump optical spectroscopy, or pump probe, I should say, optical spectroscopy, has studied paintings using that technique. And of course, Richard Ernst himself always has used vibrational spectroscopy at home to study his collection of Tibetan textiles, to establish the authenticity of the dyes in those Tibetan textiles. There have even been special issues of the magnetic resonance in chemistry dedicated to NMR in cultural heritage. The one in 2014 was co-edited by the late Donatella Capitani, whose student Valeria Di Tullio was one of our postdocs, and I'll define who we are in a minute. The review articles, the reviews by Graham Webb, for example, in the 2020 Modern Magnetic Resonance Review, there he has 4 papers dedicated to cultural heritage, one by EPR, the other 2 by solid state NMR, solution state NMR, and of course Bernhardt's paper with Maria Baillas, one of his students, using the unilateral NMR. And in fact, that was a seminal advance in the application of NMR to cultural heritage. The development of the NMR mouse by Bernhardt and his colleagues, and then later adapting that to the study of cultural heritage. Because here we had a technique now finally that is both non-invasive and portable and easy to set up. And next week, in fact, and Bernhard can tell you that himself, he's in the audience, I didn't know that he would be there. Next week there is an event at the Pratt Institute in New York called Ostia Fest, and Bernhard will be talking about the use of nuclear magnetic resonance on wall paintings at Ostia Antica. So I hope, you can participate that remotely. I plan to. The use of the NMR mouse in cultural heritage has also been reviewed by him in this book on advanced characterization techniques, diagnostic tools, and evaluation methods in heritage science. We, however, and now I'll get to who we are, decided a somewhat different tack. We used model systems to perform our studies, and chose a specific problem, the formation of what is known as metal soaps that cause the degradation of paintings. Before explaining what metal soaps are, I would like to remind you of what a painting is, an oil painting is. We start with linseed oil and a pigment to form a dye, which is laid down with a brush, of course. Linseed oil, as some of you may know, is a triglyceride. It has mostly side chain, carboxylic acid chains with at least one, and also multiple double bonds. Most of them are like that, except 7% of it is palmitic acid, and as we shall see, that's the source of serious problems. In the course of a painting, you take the triglyceride and the pigment and you paint with it, and then the system is still tacky and wet. It has to cure. The curing consists in an oxidative cleavage and cross-linking of the double bonds, which leads into a cross-linked network of the linseed oil with some side chains with unreacted double bonds. What happens later on is that the remaining double bonds oxidize a little gradually after decades or even centuries, begin to oxidize and acquire functional groups on them, like the chains acquire functional groups like hydroxyl groups, epoxides, ether linkages. The upshot of that is that what started as a hydrophobic medium gradually evolves to become increasingly hydrophilic. And now water can penetrate this network. That in itself would not be that detrimental normally. What happens though is that water causes the ester hydrolysis. Most of these chains are already anchored in place through cross-linking, so that doesn't matter really either. However, if one of those chains is a saturated acid like palmitic acid, most typically, then that is suddenly free. And now you have free palmitic acid injected into the matrix. And it wanders around until it finds some cation with which it can react and precipitate. Usually that is lead, coming from basic lead white. So the palmitic acid either finds a crystal of basic lead white, which is the most common white paint. It's a layered compound of lead carbonate and lead hydroxide. It's known as hydrocerusside technically. Or there is lead that is released into the matrix from the paint, and then the lead and the palmitic acid, lead ions and the palmitic acid and the palmitate anions come together. They precipitate. They form a nucleus, nucleation center, and then that nucleation. Then there is nucleation and growth, and you get into trouble as I will show you now. And the reason it happens is that the palmitic acid, the lead palmitate, nucleates and grows and first forms protrusions on the surface of the paint. Finally, they can even burst out of that, and in the worst case, you can have pock marks on the paint, and if there is also delamination of the paint layers, then ultimately a painting would totally deteriorate in this manner. It was first observed, this phenomenon was first observed on the famous anatomy lesson of Dr. Thorp by Rembrandt. That painting is from the 17th century, but is also seen on paintings from the 16th century, from the 19th century here, and also even in the 20th century, as these objects by Salvador Dali indicate. So the question that we're trying to study is the formation and reactions of metal soaps. By we, I mean the team that formed to study this was Sylvia Centeno from the Metropolitan Museum of Art, myself, and Cecil Dybowski from the University of Delaware, somebody who most of you know very well, who was an expert in lead NMR, and lead NMR was, after all, the technique we proposed to use to understand this phenomenon. We got our first NSF proposal funded in July, I believe it was, of 2011. And by 2012, we had we have hired our postdoc, and I'll introduce presently. And then by the time the Eastern Analytical Symposium rolled on in 2012, we already had our first results to report. In fact, that's a picture of our group at that Analytical Symposium of 2012. Standing is, of course, Cecil, You all know him. Then Sylvia Centeno from the Metropolitan, myself. Here is the next person is one of Cecil's graduate students, Fahri Alkan, who was doing his PhD with relativistic DFT calculations of chemical shift tensors of heavy metal nuclides. Sitting is another student of Cecil's, Sean Holmes, who I believe actually is at the ENC and will be giving a talk tomorrow afternoon, if I'm not mistaken. Another graduate student by the name of Yao Yao, and Anna Murphy, who was the first graduate student of Cecil's graduate student to work very intensely on this project, together with our first postdoc, Jackie Catalano, who came to us on January of 2012 from the group of Anne McDermott at Columbia University. So we were very lucky to have some great people. In fact, Jackie here, I've shown Jackie, she not only did do the first NMR work on these materials using lead NMR, but she also held the group, organized the group, mentored some of the graduate students, and she still continues to be engaged with the research of our group. Since after finishing her postdoc, she went to Montclair State University, where she is now an associate professor of chemistry and biochemistry. I have singled out a later paper of hers to introduce her work, an article in the Magnetic Resonance in Chemistry from 2020, which was also another special issue on cultural heritage science, and she wrote the article on review of the use of NMR spectroscopy to investigate structure, reactivity, and dynamics of lead soap formation in paintings. She did this work, the NMR work, together with Anna Murphy, who was a graduate student in Cecil's lab, and Anna also graduated, and she is now a member of the technical staff at the Lawrence Livermore National Laboratory. And one of the important pieces of work that the two of them did was studying the coordination chemistry of lead, of a homologous series of lead carboxylates, and correlating it with crystallography. That paper was published in 2015, I believe, in the Dalton Transactions, and here's the full reference if you're interested. And studied, as I said, a homologous series of lead carboxylates with C6, C7, C8, C9, 10, 11, and then palmitate and stearate. And empirically, what they first observed was that C6 through C8 displayed a very large lead chemical shift anisotropy, humongous chemical shift anisotropy, whereas above C9 it was a much more reduced chemical shift anisotropy. So there was a step change at n equals 9. To understand the source of this behavior, by the way, the spectra were obtained by using the Wurtz CPMG sequence popularized by Rob Shurko, and I would like to once again thank Rob after all these years for generously sharing with us the Pulse sequence program and other sage advice on how to run it. To understand this phenomenon, we have to understand a little bit about what determines the coordination geometry around a lead-2 ion. In a lead-2 ion, you have a 6s² lone pair, which normally has some p characters, sp hybridized a little bit, and therefore is what they say stereochemically active. It points towards one of the apices of the coordination polyhedron. Thus, all the other ligands point away from that, and so their distribution around the lead ion is asymmetric, and that explains, it turns out, explains the large chemical anisotropy that you see in N6, N7, and N8. And that geometry is known as a hemi-directed coordination geometry. Apparently above, and I say apparently, we'll verify that later, above N9 and above, what you see with N9 and above, you see a much narrower chemical shift anisotropy, because here we have a pure S character. The lone pair is not stereochemically active, and the distribution of ligands around the lead ion is much more uniform, and therefore the chemical shift anisotropy is smaller. That is known as a hollow-directed geometry, and all this is known to happen with lead compounds. But until then, there was no crystal. Since there was no crystal structure of the longer chains, they are very difficult to crystallize. This phenomenon was unknown for lead carboxylates. That was of course our first supposition, and then Anna Murphy was able to actually grow a single crystal of lead nonanoate, which was solved by Glenn Yupp, who is the crystallographer at the University of Delaware. And indeed, we showed the results showed that the geometry around lead was a hollow-directed or more symmetric geometry for N9. So by inference then, N9 and above adopt a hollow-directed geometry as opposed to shorter chain lengths between N6 and N8. Actually, that is this is actually the energetically normally from electronic point of view, energetically favored configuration. What happens here is that the longer chains interfere with that, so there is an energetic cost to pay if you were, and that's why the preference here is to have an pure S character, which itself is somewhat energetically higher, but is compensated by the fact that the chains now can spread out without interfering with each other. Anyway, so it is this kinds of geometric information that one would need if you were to begin to model the nucleation and growth of crystals at an atomistic level, or model at an atomistic level, the growth of small crystals in a matrix, in a pane matrix. Now, lead white is not the only source of lead in a painting. There is also another pigment called lead tin yellow, which is lead stannate, and there was long a discussion of whether lead stannate can be a source of lead, forming those lead carboxylate blemishes. Our work with model systems, it's surprising that nobody else did this before, because everybody tends to study the original paintings rather than models. We were able to show that, in fact, yes, lead tin yellow can give rise, does react with palmitic acid, and can give rise to lead palmitate. However, the material usually is a complex mixture. It contains a lot of its starting materials. So we used theoretical chemical shift calculations to identify the various products, and in that we were helped by Fahri Alkan, who did the relativistic density functional calculations on lead and tin chemical shifts on this material, and he is now at the Abdullah University in Kayseri, Turkey, as a professor. And this work was published in the journal of Physical Chemistry in 2014. This type of studies on the structure of lead carboxylates essentially were part of the first proposal that was funded, and the set proposals we obtained. But there was, in our next project was to now understand the function of water and maybe other solvents in the matrix, and also the role in facilitating formation of lead carboxylates. For that, we actually used the NMR mouse in conjunction with model systems, and for that, Valeria Di Tullio came to us from Italy as a postdoc. She had a lot of experience using the NMR mouse, and she's now, of course, for a long time now, she has a permanent job, and she's back in Italy at the Institute of Heritage Science of the National Research Council of Italy. Here you see her. This is a fairly recent picture of her that she sent me of the using the NMR mouse on the wall of the catacombs of Priscilla in the second century AD paintings, and you can see how the NMR mouse is both portable, non-invasive, and fairly easy to set up, as you can see. Several papers came out of this work. It's a second paper that was just appeared in the Microchemical Journal a few weeks ago. That's quite interesting to me. And that studies the behavior of various solvents that are used in cleaning paintings. And she studied the diffusion, evaporation, and retention of acetone, ethanol, and mineral spirits in an earlier paper of water itself in this paint layers by the NMR mouse, and in tandem with high resolution proton MAS spectroscopy. She applied quite extensively the inverse Laplace transform approach to identify several motional regions, motional regimes in the material. One has to be very careful, of course, because the inverse Laplace transform is an ill-posed, technically it's called an ill-posed problem, and I think we've tried to use the minimum number of components to explain the non-exponential CPMG curve that one obtains. There are three components that can be associated with the polymer matrix: the backbone, the chain ends, and possibly dangling chains on the side, and also a couple of motional regimes for the solvent, bound and free. In the case of acetone, we could separate that by using deuterated acetone to suppress the acetone signal and see only the signals from the backbone, from the polymer itself, and how they change with the addition of the solvent. That can also, it could be correlated also with the proton proton MAS spectra of the material, and all this is described in the Microchemical Journal article. So if you're interested, you can look that up. Actually, as I say, every branch of science today seems to be affected by what they call big science. Cultural heritage science, for cultural heritage science, big is synchrotron radiation, because of the synchrotron sources are very intense, means that we can do various studies with ever smaller amounts of material, provided the material survives the radiation. That includes X-ray fluorescence studies, XANES, X-ray powder diffraction, and also tomography, computed tomography, micro and nanotomography. The work is done. The leaders in this area are Loïc Pétrin in France, using the synchrotron Soleil at Gif-sur-Yvette. Now, Gif-sur-Yvette is probably familiar to some of you. That's where Anatole Abragam worked. In this country, such studies can be done at the Advanced Photon Source at the Argonne National Laboratory. And we've done that work in collaboration with Karen Chen-Vigat of the at Stony Brook University. And here you see her and her students. Here's Karen and her students. And here is Valeria, our postdoc at the Argonne National Laboratory in 2018. That work and they performed X-ray nanotomography on very thin slices of our model systems, and combined, and that was correlated with mouse data, as you will see. This work has appeared in scientific reports, and later on we also visited the Brookhaven National Laboratory because it's closer in 2019. We did some experiments there. You see our team there. Again, Karen was there, and Sylvia and Jackie Catalano I mentioned, and our most recent graduate student, Molly Wagner. Unfortunately, it was 2019, and when the COVID lockdown and issues came, then that research was abandoned, and I don't know that it will be picked up again. So that work has not been published. But the work at the Argonne National Labs has been published in scientific reports. So what was the upshot of that? Well, and you see it here. On the left, you see the X-ray nanotomography of a thin sliver of the model system, about a little cube at 24 micron on edge. What you see as yellow here is actually the lead white particles. This is a 5-to-1 pigment to oil mixture, and over here those tenuous filaments of green that you see is in fact the empty space or the polymer, or because X-ray. There is no X-ray contrast difference between air and polymer. So that is not pigment. What you're seeing there is not pigment. You can correlate that with the NMR mouse results. In a dry sample, you see the three peaks that I mentioned to you, the three motional regimes as resolved by inverse Laplace transform technique. What you see here is this is probably the back, according to Valeria, that's the backbone. This is the chain ends, and these are the dangling chains being the most fluid. If you now wet this sample, you get two populations of water, bound and free water, and of the three motional regimes, of the polymer, two of them are the ones that are plasticized a little bit and therefore have somewhat lengthened T2s, and important here is, I think, the fact that we observe two separate domains of water. I know tomorrow there's going to be a talk. I think in the morning there's a talk on weird water, and indeed there is a lot of weird water also in this polymeric in this linseed oil matrices. And we can also combine the mouse results, which give us information on open porosity that's available for diffusion of the water, with the tortuosity, which can be computed from the virtual cross sections of nanotomography. Just purely mathematically, you can compute those two. In other words, the amount of water, its linear diffusion, and its tortuosity can then be used eventually if one were to try to create a model of a paint, an oil painting. I mean, the idea, I guess, ultimately is to have an in silico model of a painting or other cultural heritage objects, so that we can compute their behavior in the future in response to various treatments. Molly Wagner was our most recent graduate student. She also got her degree, and she also is finishing up actually a postdoc with Aaron Rossini at the Ames National Lab. Initially, up until fairly recently, the only part of her thesis that was published was the introduction, which turns out to be one of the best introductions to review articles on NMR spectroscopy in cultural heritage science, and was published as such, as a review article. Her project was actually to study zinc NMR, because there are zincs, just like there are lead soaps, there are zinc soaps coming from zinc white, which is even more reactive than lead white. And initially, I wasn't going to say very much about it, other than that we've done experiments. This is at the hybrid system, at the hybrid magnet at 35.2 Tesla, at the Magnet Lab in Tallahassee. I've shown this spectra myself a number of years ago at the ENC. Some of you may remember. And yes, if you go from 19.6 Tesla to 35.2 Tesla, the spectrum of zinc octanoate collapses, sort of narrows, because the second order quadrupole interaction, as you know, is inversely proportional to the field. But just last Thursday, her paper has now been finally accepted at the Dalton, and appeared online in the Dalton Transactions. And she has done, and it reports on a very large number of zinc carboxylates, and correlates and shows shows that some of them are crystallographically known. So she has computed theoretical and experimental data of the EFG tensors. I'll leave it at that. The paper is online. One last paper by her. And that goes back to the idea of that model systems also allow you to use a very classic approach, classic strategy of NMR, using essentially isotopically labeled materials. Jackie Catalano had used deuterated palmitic acid and lead palmitate to study the molecular dynamics of these materials in the cross-linked linseed oil films. That was published back in 2017 in solid state nuclear magnetic resonance. Valeria, as I mentioned, used deuterated acetone to gain some selectivity, and Molly actually used carbon-13 labeled palmitic acid to monitor the kinetics of zinc palmitate formation in a modeled paint layer with zinc oxide. And in fact, she did that as a function of various relative humidity, and she was able to model her kinetic data with a single model, just adjusting parameters for various relative humidities, and that paper has not been published yet. We're just beginning to write it, and so I prefer not to say any more about that. I don't want to steal her thunder. That's a very interesting paper. When it appears, it will teach us something about the actual kinetics of the process. I would like to conclude now with some personal thoughts about the longer range prospects of NMR spectroscopy in cultural heritage science. These are my own private thoughts. They may not even reflect the thoughts of my colleagues. But I always say that any objective assessment must begin by acknowledging weaknesses and while emphasizing strengths. The major weakness of NMR, we all know it, we lament it every day. It's the low sensitivity, the low intrinsic sensitivity, and it will remain a persistent problem regardless of in my judgment at least, regardless of advances in hyperpolarization. Furthermore, when when adequate sample removal is permissible and an NMR spectrum can be obtained, it is generally desirable that the sample retain its integrity for future measurements by other techniques. So dunking the sample into DNP juice is not going to happen. The major strength of NMR, we all know it, is that it provides exquisite detail about structure and dynamics at the molecular level. Well, actually, there are certain trends in cultural heritage that are going our way. Replication experiments and model systems are finding increasing use as tools for gaining deeper understanding of the physical and chemical processes associated with the production, interactions, and aging of cultural artifacts, and of the techniques used by the artisans and artists who produce them. So there is a lot of activity in models, systems, and replicates, regardless of any of our activity in NMR. That's an independent process that's happening. Obviously, studies of replicates and model systems are not sample limited, and I believe it is here that NMR can become part of the analytical toolkit of the cultural heritage scientist. Well, what do you hope to learn? I think some possible generic questions that could take advantage of recent advances in NMR could include organic surfaces, inorganic interfaces, and transport processes through porous materials with interactive pore surfaces. In other words, pore surfaces that are not inert, that interact with the solvent or the water, and that can have an impact on the properties of the system. Well, I think I'm going to stop at this point, and entertain. I'd be glad to entertain any questions. Thank you.
Okay, thank you, Nick, for a great talk. So questions?
Yes.
Alexei, yes, from Texas. Okay, I have technical questions. I saw they use the NMR for the geometry, right, about iron and the lead. So why not to use the EPR?
The EPR?
Yeah.
For which
For the
material?
geometry, right? Geometry around these metals.
Oh yes, I'm sure that there is a whole body of EPR in cultural heritage science. Most of these metals are diamagnetic. I mean, at the moment we have zinc and lead, and they are diamagnetic, so they are not. They don't have a free electron spin. But certainly there are other instances where paramagnetic impurities or are involved. So EPR is not is not strange to cultural heritage science. But I don't think we have instances where we have EPR active centers. Do you have anything specific in mind?
Not really. I'm only worked
Okay.
with the cobalt and the copper before, so.
Oh, that's different. There are, I mean, that's a very interesting question that you raise, because in fact, in a totally different area, there is one, of course, has copper in some of earlier pigments, some ancient pigments. And this gives me an opportunity to mention this because it's going to be mentioned next week at the Ostia Fest in conjunction with the Egyptian blue, a material called Egyptian blue that is actually a copper calcium silicate. A large number of years ago, many years ago, I looked at the silicon NMR of that material, both for what is known as copper, what's known as Egyptian blue, which is calcium copper silicate, and there is also a Chinese counterpart called Han blue, which is the barium containing copper barium silicate. Well, curiously enough, the silicon in that material shows a very large pseudo contact shift from copper, and it's different from Han blue and Egyptian blue. We never, at the time, it was over 20 years ago, I noticed that I did that study. We never really explained the difference, other than to say that probably this would be a function of distance between copper and silicon. But there isn't much difference in the two, and I wonder if the other issues, spin orbit coupling, things like that, and I'm not familiar with the theory behind the paramagnetic systems, but whether they impact this. But the pseudo contact shift between copper and silicon in the two materials is vastly different. I mean, the chemical shift difference is like 500 ppm downfield in one case and only 300 ppm in the other case. So yes, there is a lot of work to be done there with not all with EPR, but also with NMR of paramagnetic systems.
Okay, I see.
But
Okay,
no.
yeah, thank you.
Nick, maybe I should add that Joseph Hornack actually has built an EPR unilateral sensor
Oh, yes.
and
Yes.
applied it to cultural heritage studies. Maybe that should be mentioned in that context.
Oh, absolutely, you're absolutely right. I didn't mention that. Of course, I know Joe very well. I provided him with some of the samples that he ran, and we did some work together initially. I'll tell you what the difficulty with that is. I tell you why I have stepped back from that work. I was interested in that for my other set of interests, not this, but from ceramics point of view. And in many ceramics, the material is not uniform, is not oriented properly, is not powder-like. It has some residual orientation. And because of the way the clay lies down and the way that it's treated when you throw clay, how the platelets orient themselves and so forth. And I noticed, and the way we were doing the experiment at the time, Joe had built a large solenoid, and we're doing surface coil studies. And I noticed that the slightest motion of the orientation of the sample in the magnetic field changed the spectrum dramatically. Don't forget, obviously, you know that better than I do. At those low fields, the crystal field interactions are much stronger than the electron-Zeeman interaction. and so the high field approximation breaks down. You have a very complex set of new set of eigenfunctions and so forth. Analyzing those spectra must be a nightmare. I gave up. I looked at the complexity of the theory behind it and gave up, frankly. But I don't know, maybe some fingerprinting may be possible by that technique. What is your feeling of that? You know, he moved away from the fixed solenoid, and he has developed the equivalent of your system, of an EPR mouse, except that mouse does spectroscopy rather than dynamics.
I don't know too much about it. I just know that he has a couple of publications in the cultural heritage field, and he is able to, for example, discriminate between the color on or the pigments in different bills and other objects of cultural heritage. So it's kind of cute. But I thought you would know more of where that is being used. But
yes, I was I was there when he was doing the experiments. We did some experiments together, but my concern is that what he does, and it would be nice if it worked, is spectroscopy, and spectroscopy of EPR spectroscopy at that lower field strength is very complex. Very
yeah,
complicated.
I understand the complications. Thank you.
Yeah.
More questions?
Nick, absolutely fantastic talk. We very much appreciate it. My question for you, Nick, is how much of your tenure at the old Eastman Kodak company, obviously a bit of a connection to the arts, how much did that influence your decision to move into the field you're in today?
Not as much as you might think. Now, you may think, of course, I was at Kodak with color photography, where our preoccupation with dyes and pigments, I should be interested in that. After all, dye fading, right? I mean, the Dye Permanence Institute at RIT and Kodak worked with them, both in image dyes and in chemical photography, as well as the fading of inkjet dyes that were of interest to us later on. Actually, at that time, my interest was not in art, curiously enough. I thought that after retirement, I would do a lot more in historic preservation. We live in a historic house here, listed on the National Register, and so forth. And I thought I was going to devote my time in combining photography and ancient pictures with local history and historic preservation and so forth. That did not work out for a number of reasons. I lost interest in that, and my primary interest was actually in ceramics, and still is. I was telling some of you earlier today that most of my research now is in ceramics history, and that's what I talked about at the meeting in Indianapolis, and as Bernhard remembers, but it was my collaborations, my association with Silvia Centeno, and then bringing on board Cecil that took us in that direction. For the work that I described today, the big influence on me was, in fact, Silvia Centeno at the Metropolitan.
So, other questions? So I really appreciate. Thank you very much, Nick, for a great talk into an area that I knew very little about before tonight, and I think some of us are the same. So let's give our thanks to Nick.
Thank you.
Okay. Thank you.
Nick, absolutely fantastic talk, and on behalf of the Ivan Board of Directors, you've concluded very nicely for us. the ENC Eisenhower meetings. And what a conclusion at that. Thank you very much, Nick.
Well, thank you for asking me, and I hope people found that interesting and stimulating. I hope somebody decides to work in this area, at least part-time. At some future.
And I will thank you for staying up so late tonight.
Yeah, it's almost midnight now, but it's, as I said, it's way past my bedtime. It doesn't matter anymore. Okay, great. Thank you.